Hello students, today in this lecture we are going to cover conclude with the same topic that we have taken in our last lecture, that is the formulation of admittance matrices for the electrical networks. Okay, and in the last lecture we have taken one direct method to formulate the Ybus matrix by using the mutual admittances, transfer admittances, driving point admittances and so on. And so now we are going to start with the formation of Y-bus matrix using singular transformation method. Okay, and here again we are taking the same example of a 4-bus system, and in which each bus is connected with the other, but there is no connection between the bus 1 and bus 2. Okay, and the generators are connected to each bus, and demand is also taken from each bus. This SD represents your demand power and SG represents your generated power. Okay. And the first step to in this singular transformation matrix is to draw the linear graph of this circuit given. Okay. And for drawing the linear graph, just take the buses as simple nodes, like this node number 1, node 2, node 3, and node 4. These are our 4 buses. Okay. And one reference node is taken, 0. Okay. And this one is our reference. Now, each node, each bus is connected with the reference node also. So, node 1 is connected with 0. Node 2 is connected with 0. Node 3 is connected with 0. And node 4 is connected with 0. This is one is the same as we have done earlier in the previous method. And there is connection between internodes also. Like here is the connection between 1 and 2, between 3 and 4, between 2 and 4, between 1 and 3, and then 2 and 3. Okay, similarly, these are the branches, various branches are connected. So this 1, 2, 3, and 4, these are called, and this one 0, these are called as nodes, and these one arrow points, arrow 1, 2, 3, 4, here is 5, 6, 7, 8, and 9. These are called as branches. So this means that in this linear graph, there are 5 nodes and 9 branches. Okay, as you see here also, there are 5 nodes, 1, 2, 3, 4, and 0, and there are total 9 branches. Now let me read this definition. A linear graph depicts the geometrical introduction of the elements of a network. A graph is connected if and only if there is a path between every pair of nodes. Okay? So this one is called as the connected graph, which means that each node is connected with any one of some other node also. Okay? No node remains as open. Okay, whether there is no connection between 1 and 4, but the 1 has its connection with 2, 3, and 0. Okay, that means the node 1 is not a separate node, it is connected with other nodes. So that's why it is called as the connected linear graph. If each element of a connected graph is assigned a direction, it is called an oriented graph. As you've seen here in this figure, that each branch, this one is called as branches. Each branch is assigned some direction. Like here, there is a direction between 1 to 0, towards 0. Okay, here number 2 branch is also towards 0. And like this number 5th branch. 5th branch is from 3 to 4. Okay, 6th branch is from 3 towards 2. Okay, branch number 7 is from 1 towards 2, like this. Okay, each branch is assigned with some direction. So that's why it is called as a connected graph, or it's also called as an oriented graph, because there is some orientation to each node. Okay, some direction is assigned to each node. That's why. Now, out of the m total nodes, one node, normally described by 0, is always at the ground potential. Okay, and the remaining n, that is m minus 1 nodes, are the buses at which the source power is injected. Okay, so in this figure, there are n buses. What are the total number of buses? N, and that n is equal to 4. And total number of nodes, that is m is equals to n plus 1. Okay, so this 0 node is called as the reference node, and this one is at the ground potential. Okay. This combination is described under the subheading primitive network. Okay, this one is also called as the primitive network. A connected subgraph containing all the nodes of the graph but having no closed paths is called a tree, like this figure. Okay, this one here, the nodes are only the buses 1, 2, 3, 4 and 0. Okay, and the branches are only 1, 2, 3 and 4, which are connected with the ground potential only. Only that branches are taken here. Okay, so in this graph, this one is called a connected graph, but there is no closed path in this graph. Okay, there is no closed path. So this type of graph is called as a tree. This one we called as tree. The elements of tree are called as branches or tree branches. Okay, here we call them as 1, 2, 3, 4. We call them as branches. Now the number of branches B that form a tree are given by B is equals to M minus 1. M is the number of nodes, total number of nodes minus 1, that is equal to N. So how many branches are there in this linear graph? There are total branches that are equal to the number of buses. Okay, if it is a 4-bus system, then the branches are 4. If it is a 5-bus system, then the branches are 5 accordingly. Okay, so here only that branches are considered which are connected to the reference bus only. Now, those elements of the graph that are not included in the tree, this portion. Okay, this portion is not included in the tree, but is a part of linear graph. Is a part of linear graph. So those elements of the graph that are not included in the tree are called as links because it acts as a link between the two nodes. Okay, these are called as links or link branches. Okay, overall, you can call all of them as branches, but specifically these are called as tree branches and these are called as the link branches. Or simply you call these as branches and these as links. Okay. And they form a subgraph not necessarily connected, called co-tree. So this type of graph we called as the co-tree. So a linear graph consists of a tree branches and link branches. Okay, this portion is called tree and this portion is called as a co-tree. The number of links of a connected graph with E elements is given as L is equals to E minus B. What is B? B is the number of branches. That is the number of buses. Okay. It is further equals to E minus, what is B? B is M minus 1. So just put down here the value of B if it comes out to be E minus M plus 1. Okay. And what is E? E is the number of elements, 9. So how you calculate 9? From this linear graph. Firstly, what is the first step? The first step is to convert this network one-line diagram into the linear graph and count all the elements. Okay, like 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you can count all the connections between the nodes. Okay, so the number of elements are 9. Okay, like this. So here is the notation final. So E is equals to 9 as seen from the linear graph. M is equals to 5, that is the total number of nodes including one reference node. B is equals to number of branches, that is M minus 1, that is 5 minus 1 equals to 4, that is equal to the number of buses. And L is equals to the number of links, that is E minus B. E is the 9 and B is branches. So 9 minus 4 comes out to be 5. So there are total 5 links. Okay, 1, 2, 3, 4, 5. Okay, so In this linear graph, there are 5 links and 4 branches. So in this way, how the one line diagram is converted into the linear graph of the circuit. Okay. Now next is the primitive network. So just the basic introduction about the primitive network. The alternative impedance and admittance form the representation of a journal network element. So this one is a journal representation for any element or any source. The impedance form is a voltage source in series with an impedance. Okay, so impedance is always converted into the voltage source in series with impedance, whereas if there is admittance, then it is converted into the current source in series in parallel with the admittance. Okay, like this. So the element current IRS and the element voltage VRS is equals to ER minus ES. Okay, this we have already applied while applying the Kirchhoff's law in the Ybus formation. Okay, so the receiving end minus the sending end. Okay, like in this figure, in this linear graph, here bus node number 4 is the receiving node. Okay, and node number 3 is the sending node. So what is the voltage level between them? So that is V4 minus V3. Okay, receiving minus sending. So here it is ER minus ES. The net voltage appear across this impedance. Okay, so similarly, the same voltage across this admittance is again ER minus ES. And what is the final equation? So it is VRS plus ERS is equals to ZRS into IRS. Here RS are the simple receiving and sending ends. Okay, the potential difference between the receiving and sending end, that is R and S. Z is impedance, I is the current, and V and E are the voltages. Okay, and similarly here for the admittance form, if the numerical is given in this form, then it is taken as IRS plus JRS. J is also the current and is equal to admittance, that is YRS into VRS. Okay, V is the voltage, Y is the admittance. So in this way, it can be, it is a journal notation for the any network elements, and this JRS is equals to minus YRS into ERS, or YRS is the reciprocal of impedance. Okay, and the same equations in journal can be written as V plus E is equals to Z into I, or I plus J is equals to Y into V. Okay. Z and Y are referred to as the primitive impedance and admittance matrices respectively, and they are reciprocal of each other. Okay. Now next one. So this one is our tree. Okay, and this one is our core tree, and this is the notation. E is the number of elements, M is the total number of nodes, B is the branches, L is the links. Okay, now we obtain the following relation between the 9 elements. So the total elements forming the tree and core tree are 9. 9 elements are there, and the 4 bus voltages V1, V2, V3, and V4. And apart from these, there is one reference voltage also, ground potential. So how to now how to draw the bus incidence matrix A? So for this bus incidence matrix, this one here on these row sides, so there are total 9 rows, that is equal to the number of elements. Okay, total 9 rows are there, number of elements, and number of columns are 4, that is the number of buses. Okay, so the total number of buses are 4. So this one, and like you see there here that the bus element number 1. Okay, element number 1, what is the potential? This one 0 point is at the ground potential, and this is at the V1. So VB1 is equals to V1, and similarly And similarly, VB2 is equals to V2, this one for branch 2, and VB3 is equals to V3, and VB4 is equals to V4. Okay, so this one is because their one node is at the ground potential. So that's why here the simple voltages are applied V1, V2, V3 and V4. Now for the link 5, this one VL5. Okay, VL5 is this one V3 minus V4. Okay. Similarly, VL6 is V3 minus V2. Okay. VL7 is V1 minus V2, and VL8 is V4 minus V2, and similarly VL9 is V3 minus V1. Just see the directions and write these voltage equations accordingly. Okay, now you have to convert these equations into the matrix form. Okay, so there are 4 voltages V1, V2, V3 and V4 for the 4 buses, and there are total 9 elements. Okay. Branch 1, only V1 is present, 1 is present, the rest are 0. Okay, for branch 2, only V2 is present, rest are 0. For branch 3, only V3 is present, rest is 0. Okay, similarly for branch 4. Now for the links, for link number 5, so V3 is positive 1 and V4 is minus 1. Rest is 0. And similarly for number 6, V3 minus V2. V3 is plus 1 and V2 is minus 1. For 7th link, it is V1 minus V2. Okay, for 8th, it is V4 minus V2. V2 is negative, V4 is positive 1. And similarly for L9. Okay, so and this one is called as the bus incidence matrix A. Okay, this is called as bus incidence matrix A. And how it can be written? On the column side, there is a number of buses. On the row side, there are the number of elements. Okay, and the matrix consists of this upper, this one is for the branches, and the lower one is for the links. Okay, and you generally see that the matrix appear for the branches is generally an identity matrix. Okay, it generally comes to be an identity matrix with only one element, unity on the diagonal elements. Okay, unity is there on the diagonal elements, and the lower one is the matrix for the links. Okay, so here V is equals to A into, now next what we have to perform, V is equals to A into V bus. What is A? A is this one. Okay, let's see further. Now this matrix is a rectangular and therefore a singular. Its elements Aik are found as per the following rules. Aik is equals to 1 if the ith element is incident to and oriented away from the kth element. Okay. Its value is 1 when it is incident away from the kth node. Like here it is. Okay. It's 1 for 3 and minus 1 for 4. So this is the rule. Okay. And minus 1 if the element is incident to but oriented towards the kth node. Okay, and it is equals to 0 if the element is not incident to the kth node. If that element is not connected with the kth node, then it is taken as the 0. Okay, so now next is substituting equation 2 into equation 1. Like this one, this is our equation number 2. Okay, and here this one is the equation number 1. Okay, I plus j is equals to y into v. Okay, you have to put down the value of v here, this one, at here, this place. So I plus j is equals to y a into v bus. Okay, this one, a into v bus, and pre-multiplying the equation number 3 by at. At is the transpose of the bus incidence matrix. Okay, pre-multiplying both sides. So A transpose into I plus A transpose into J is equals to A transpose Y A B bus. Mark it as number 4. Now each component of the n-dimensional vector A transpose into I, this one, is the algebraic sum of the element currents leaving the nodes 1, 2, 3, 4 to n. Therefore, as per Kirchhoff's law, current law, the A transpose into I comes out to be 0. Okay, so this comes out to be 0. So we are left with only A transpose J and this term. Now, similarly, each component of the vector A transpose into J can be recognized as the algebraic sum of the source currents due to this J injected into the nodes 1 to 3 up to n. So these components are therefore the bus currents. Hence, we can write this as J bus. Okay, so this is the matrix that related to the current injection into the bus. Now mark it as number 5. Now equation 4 can again be written as J bus is equals to A transpose Y A into V bus. Or we have Y bus is equals to, so what is J bus? J bus is equals to Y bus into V bus. Okay, so Y bus comes out to be equal to A transpose Y into A, as Z bus is the inverse of Y bus, that we know. Okay, so how this final comes out to be, just put this J bus is equals to Y bus into V bus, and the V bus cancel on both sides. So we are left with Y bus is equals to A transpose Y into A. Now this we have to verify through our final one derivation that we concluded on the board now. Okay, so in this we have to formulate the Ybus matrix using singular transformation method. Okay, and we are going to apply this method on the same network of the 4-bus system. So for that, firstly we convert that 4-bus network into the linear graph. So this one is called as linear graph. Okay, and as we have seen in the PPTs that for this network we have to verify that Y bus is equal to, yes, Y bus is equals to A transpose into Y into A. Okay, and what is A? A is called as the bus incidence matrix, which we have recently seen in the PPTs. So we have to prove that Y bus is equal to A transpose Y into A. And what is the formula for Y bus? We know. We have earlier derived in the previous lecture during the first method. Okay. So firstly, we have to write down the A transpose like the bus incidence matrix. So for A, you have to write the matrix first, and on the row side there are the total number of elements 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, the total number of elements in this linear graph are 9 elements with 4 branches and 5 links are there. Okay, so the number of rows be equal to the number of elements, that is 9, and the number of columns are 4, 1, 2, 3 and 4. Okay, that is equal to the number of buses. Now you have to check from this linear graph that how the connections are there between the bus 1 and the element 1. Okay, like bus 2 and element 2. Now, as seen from this linear graph, the bus number element 1, this one, is connected between the node 1 and node 0. Okay, so the first element here entry is 1 and the rest of the entries are 0. Okay, similarly for the element number 2, this one, it is connected between the bus 2 and reference node. So here it is 0, 1, 0 and 0. And similarly for the third element, it is connected between third bus and 0. So it is 0, 0, 1 and 0 like this. And similarly the fourth element, it is 0, 0, 0 and 1. Okay, now this type of matrix, it is only for the branches, not for the links, it is only for the branches, and this type of matrix generally appear as an identity matrix. Okay, it generally appear as an identity matrix. Now we have to write the same matrix for the number of links in this co-tree. Okay, this arrangement is called as a co-tree. Now, as you see here that the element number 5, okay, it is V3 minus V4. Okay, so it is connected between node 3 and node 4. So the entry for number 1 and 2 is 0. Entry for 1 and 2 is 0. And here it is 1. And here it is minus 1. Okay, and similarly for the node 6, it is connected between 2 and 3. So this one is 0, this one is 0, and it moves from V3 to V2. V3 minus V2 is there. So this one is 1, here it is minus 1, like this. Okay, similarly for link 7, so it is between 1 and 2, that is V1 minus V2 is there. So here it is 1, here it is minus 1, and these two are 0. And similarly for node 8, element 8, and this is V4 minus V2. So V4 is 1, V2 is minus 1. So these are 0, like this. And finally, the element number 9, and it is connected between 1 and 3. Actually, it is V3 minus V1. So V3 is 1, V1 is minus 1, and here it is 0. So this is called as bus incidence matrix. Okay, this is called as bus incidence matrix 8. Okay, now next step is we have to write down the primitive matrix. So what is primitive matrix? This one, Y. Okay, now to write down Y, that is the primitive matrix, and this matrix is a square matrix of the number of elements. Okay, it depends upon the number of elements. So just 1, 2, 3, 4, 5, 6, 7, 8, and 9. As the total number of elements in this linear graph are 9, so we have to take accordingly the 9 rows and 9 columns will be there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Okay. Now in this, like the first element, this one, this is the first element, and the first entry for the bus, this primitive matrix is here. We simply write as Y1 0 because it is connected between the node 1 and node 0. That's why I have taken 1 0 and write the rest as 0 0 enter. Okay. Now similarly, the second element is 2 and 0. So 0 here we write as Y2 0, and the rest simply write as 0. Okay, and similarly the third entry, it is 3 and 0, and just 0 0 Y3 0, like this. Okay, similarly now fourth is between 4 and 0, just mention them as Y4 0. Okay, now the fifth entry is this one. Okay, this link, fifth element is, it is between 3 and 4. Okay, the fifth element is between 3 and 4. So just write like this 0 0 0 0 Y3 4. Okay, but in actual practice now, here the values are given. In actual numerical, here the values are given for these admittances. Okay, then you have to apply that values here. Right now the sixth element is between 3 and 2. So y3 2 0 0 0. Now the seventh element is between 1 and 2. So write y1 2 0 0. Eighth element is between 2 and 4. y2 4 and 0. Ninth element is 1 and 3. So y1 3. So this one is your primitive network. Okay, so this one is your primitive matrix, and this is called as primitive matrix. And one thing you observed from this matrix that all the entries are on the diagonal. Okay, the rest of the off diagonal elements are all 0 for the primitive matrix, and all the entries be there on the diagonal entries. Okay, and how many entries are there? The total number of elements in the network. Okay, so this one is a bus incidence matrix, this one is the primitive matrix. Now you have to perform these calculations. Okay, firstly, take the transpose of this bus incidence matrix, multiply it with y. Okay, post multiply it with y. Okay, I'm just going to write it down like this. So as we have to prove that Ybus is equals to A transpose Y into A, so firstly we do the calculation of this bus primitive matrix with the bus incidence matrix. As this one is 9 by 9 and this one is 9 by 4, so we got this answer upon multiplying the primitive matrix with the bus incidence matrix, and here we got the result in the form of matrix 9 by 4. So this one is our 9 by 4 matrix, which is achieved after doing the calculations of y into A. Now we have to multiply this with A transpose. Okay, multiply with A transpose. So what is the transpose? That is just the shifting of rows into the columns and columns into the rows. Okay, now finally A transpose, as we know that the A matrix, that is bus incidence matrix, is a 9 by 4 matrix. So A transpose comes out to be 4 by 9 matrix. Okay, A transpose comes out to be 4 by 9 matrix, and this Y, which we have recently calculated, this one is the 9 by 4 matrix. Okay, and when you solve it, you got this matrix as 4 by 4 matrix. Okay, and this method, that means the complete A transpose Y into A. Okay, and what is the final answer for this is? The final answer for this comes out to be, here it is y10 plus y12 plus y13. Okay. Next element is minus y12 minus y13, and here it comes out to be 0. Okay, similarly next, here it is minus y12, here comes out to be y20 plus y23 plus y24 and plus y12. Okay, because we know that the node second is connected with all other nodes also. And here the next element is minus y23, and here it is minus y24. Okay, and next row it comes out to be minus y13. Here comes out to be minus y12 2, 3. And for the third entry, here comes out to be y3, 0 plus y1, 3 plus y2, 3 plus y3, 4. Okay, and this fourth entry comes out to be minus y3, 4. Okay, this is the separate one. Like this. Okay, here it is the separate one. Okay. Now the final row entry comes out to be here, as there's no connection between 1 and 4. So this element comes out to be 0, but it also appears while doing these calculations. Okay, it also appears while doing these calculations also. So here it is minus y2, 4 minus y3, 4. And the final entry comes out to be y4, 0 plus y24 plus y34. Okay, as no connection is there between 1 and 4, so this will be the final matrix. And we have seen that this matrix appears to be the same as which we have got in our first method. Okay, which we have got in our direct method of Ybus formation. So this method appears to be the same. This matrix appears to be the same. So while performing these calculations also. So this is the another method to calculate the Ybus method. That is a singular transformation method.